This is just a little extra part to the Newton's second law video. As promised, I'm going to do one more example. It's a two-object example that includes some of the things that we've done in the previous examples. Okay, so we have a 10-kilogram block sliding on a frictionless incline. The incline makes an angle of 60 degrees with respect to the horizontal, but it's then connected by a light rope over a pulley, which we should probably also say is a light pulley with no friction. And that pulley is up at the top of the incline, and then it's holding an 8-kilogram block hanging downward. So the picture looks like this. We have an incline, which I guess should look a little bit steeper than that, but oh well. And it has an angle, which I'll call theta, of 60 degrees. We have one object, which we could call MA, for example. And MA is equal to 10 kilograms. So that's sliding along the incline, but it's connected by a rope, which is going to go over a pulley and connect to a second object. So there's a pulley here. And that second object we could call MB, and it was 8 kilograms. Okay. Now, I could draw the free body diagram on here. It doesn't look like the objects are close enough to make it confusing. So let's draw the free body diagram for each object. We'll put a dot on the center of each object and then draw the forces that exist. So starting with MA, well, it has mass, so it should have a force of gravity that points downward directly. And I need to give it a unique name, so FGA. It's in contact with the ramp, so there's this surface of contact here, so there should be a normal force which is perpendicular to that surface of contact. So let's call that Fn, and there's only one normal force in the whole problem, so I'll just call it Fn. I don't need to call it Fna. And then there's a tension force that's pulling along the rope, so I'll call that FTA. And these are all vectors. Let's do the forces for mass B. So there's a tension pulling on that as well. I should not give it the same name as FTA because, well, it acts on a different object and it points in a completely different direction than the previous vector, so I'll call it FTB. And then that object has mass, so it also has a force of gravity, which points down, which I'll call FGB. My free body diagrams are not done yet. Why? You tell me. You can't tell me? Okay. They're not done yet because remember, the free body diagram represents Newton's second law. So for example, for MA, we have F net A is equal to MA AA. And if it's going to represent Newton's second law, it should represent both sides of Newton's second law. So I want to draw the acceleration vector as well for each object. So this is a case where I don't actually know where the acceleration vector points. For the object on the incline, the acceleration vector should either be pointing in this direction or it should be pointing in this direction. So I know that it's going to move along the incline, so the acceleration should be either backwards or forwards on the incline, but I don't actually know which way it goes. So this is sort of an additional trick that you need to know, which is you just make a decision, executive decision about the way that the acceleration is going to point. And if you remember, when we solve the boxed equations, we're solving only for positive constants. So in those boxed equations, we'll get an acceleration value. And it should be a magnitude, it should be a positive number. If it turns out in the very end that the acceleration value turns out to be negative, then we know we made our wrong choice back at the beginning. We know that the choice we made about the acceleration was in the wrong direction, And therefore we just say it. We say, oh, it's not accelerating that way, it's accelerating this way. We don't have to change anything else. Everything else will be fully consistent. We'll get all of our answers, but we just know that the choice that we made in the beginning was wrong. So all I have to do is make a choice, and I'm going to say, I don't know, I guess I'll choose it to go up. So, I mean, you see sort of the competition here. We have a heavier object on the incline, but the lighter object is sort of pulling directly down instead of at an angle, so I'm not sure which one wins in the end. Now, the acceleration of block B, however, now is completely determined. So both its value and its direction are determined. If these objects are connected, then we know that if the one is going up the incline, then this one must be going down in space. So, so we draw it. So I'm going to draw the acceleration vector of B, and it's pointing down like that. And we know something else. If they are connected, then that means that they have exactly the same speed at any moment, and the way that the speed is changing is the same at every moment. So the magnitudes of the accelerations are also exactly the same. So this is a new thing, and we should write this down as an equation, which is magnitude of the acceleration for A is equal to magnitude of the acceleration of B, and we could just call both of them A. So there's a single magnitude of acceleration, which I can call A. If you remember from the previous problem, there's something else we can say, which is about the tensions. So this force, this tension force, is definitely not the same force vector as this one, but we have a rule that the magnitude of the tension along any rope, as long as it doesn't have much mass and as long as the pulley doesn't have mass or friction, the magnitude of the tension is the same all along the rope. So I have an additional statement, which is the magnitude of the force of tension A, let me write that a little more clearly, is equal to the magnitude of force of tension B, and again I can just give it a single name. We'll call it the tension in the rope. We might call it the tension in the rope. Okay, I think we're ready to start now. So I've already written down Newton's second law for the first object, so let's continue. We choose a coordinate system. As we saw in a previous example, when you have an object on an incline, this is often a nice coordinate system to choose because you get multiple things on the x and y axes. The only thing that falls off of the axes is the gravity vector, and we'll deal with that separately. So we have Newton's second law is a vector equation. For this object means the normal force plus the force of gravity on A plus the force of tension on A is equal to the mass of A times the acceleration of A as a vector. So I've taken the equation sheet equation, the general law of nature, made it specific to my free body diagram. And now I look at it on the coordinates. So I'm just going to look at the x's first. This is the don't think step. I just rewrite. So I make each vector an x component. And I guess this is the think step, where I have to look and see what each component is. If I look at Fn, the x component of that vector, well, this vector points along the y direction, so it has an x component of 0. So I can plug in 0 there. FGAX, if I take that vector and place it on the coordinate system, it points neither along the x nor the y, so I need to actually figure out what it is. So let's give ourselves a nice big coordinate system to find it. So my FGA vector points down, which with respect to the coordinate system looks like this. I'm looking for the x components, so project back to the x-axis. It's this tick mark, FGAX. What do you see about that component immediately? Well, you see it lies on the negative x-axis, therefore it's going to be a negative number. But I need to find out what its absolute value is from this triangle. So the triangle I'm going to use is a right triangle that looks like this. So the hypotenuse, as always, is the magnitude of the vector. I'm looking for this side, the x side. And then we need to go through that process of finding the angle that was given to us. So as I showed you last time, I think it's easiest to draw a horizontal here. And then you see that the angle that the x-axis makes with the horizontal is exactly the angle that the ramp makes with the horizontal. So this angle here is what I called theta, 60 degrees. This is a right triangle, so that means that the angle up top is not 60 degrees. That means that 60 degrees is this angle here. So I can put that in my triangle, theta, and then I can find that component. So we have opposite over hypotenuse, so sine theta is equal to x over magnitude FGA, or x is equal to FGA sine theta. And now I'm ready to plug it back into my equation up here. I just need to make sure to remember that my tick mark sits on the negative x-axis, so this is going to be minus FGA sine theta. Moving on to the next vector, FTAy. That's an easier one. That points exactly along the x-axis, so we have plus the magnitude of FTAy. And then we have the acceleration. Give myself a little more room. So the acceleration is not 0 here. I have to find it. We have to find the x component of the acceleration of a. I don't know why that looks so terrible. M-A-A-A-X, that's what we're looking for. So what is the x component of the acceleration? Well, I look at this vector with respect to this coordinate system. I see it points along the positive x-axis. So the x component is simply the magnitude of the vector. And that's it. I write a boxed equation. So let's get rid of that minus. So we get FTAy. But for FTAy, I have a name for it already. Remember, I said that all of the tensions have the same, are the same magnitude. So I can just write that as T, and then I have minus FGA. Well, FGA I have an equation for. That's going to be MAG times sine of theta, and that's equal to the right-hand side, which is MA times AA. So there's a boxed equation that we have. Okay, we're definitely not done yet. We have lots of unknowns, the acceleration, the tension, so we need to keep going, and we'll keep going by doing the y equation. So the y equation for the same vector equation is, don't think, just write fny plus fgay plus ftay is equal to ma aay. Now we look at our components and find them. So fny, well, that vector points along the positive y-axis. So I could draw it for you here. So here's our positive y-axis, and the fn vector points along it. That's fn, and its y component is this number, fny. So that number is a positive number, and it's exactly equal to the length of the vector. So that's what we write. So we write fny is positive fn. fgy, well, that's going to be this number here, this tick mark, fgy. That's going to be a negative number, and we can find it from our triangle. So looking for the side y, we have cosine of theta is equal to y over fga, and therefore y is equal to fga cosine of theta, and therefore we plug in, reminding ourselves to go back to look at the actual component, the tick mark, which is negative. We write minus fga cosine theta. Then we have FTAy. Well, FT points along the rope, which is also along the positive x-axis. So it has a positive component equal to the magnitude. So it's just FTAy. And then we have MA. Don't stop until you finish the whole equation. And we have AAY. So what is the y component of the acceleration vector of object A? Well, that's this vector placed on this coordinate system. You can see it's going to have a 0 y component. So this becomes times 0. So our next boxed equation is going to be Fn is equal to, let's move everything else to the other side, FGA, oh, but I can write that in terms of the magnitude of the force of gravity, so MAG cosine theta, and then minus FTA, but I can write that in terms of my definition for the magnitude of the tension, minus T. There we go. I still think we're not ready to solve because remember we have an unknown tension, we have an unknown acceleration, we still have the unknown tension, but we also have an unknown normal force. So we're not done yet, but luckily we still have another object. So now we can do MB. So this was MA, and now we're going to do MB. MB has this nice simple free body diagram. Do I have space down there? Maybe I should copy it. So let's move this out of the way. And let's copy our free body diagram. So don't need any of that stuff. So here's our free body diagram for MB. We write down Newton's second law. F net B is equal to MB AB vector. We make Newton's second law specific to this problem, to this free body diagram. So that's going to be FTB vector plus FGB vector is equal to MB AB. We choose a coordinate system. So we can choose any coordinate system we want. I don't have to go back and use the previous coordinate system. So I don't know, let's choose this coordinate system where the y-axis points up now. And you see I don't have to do anything about the x direction because I don't have anything pointing in the x direction. So my don't think step is just one. I just write out the y equation. FTBY plus FGBY is equal to MB ABY, and then I find the components. So we have FTBY, the y component of this vector. Well, it points up, and the y-axis points up. So that's just going to be the magnitude of the vector, FTB. FGBY, well, FGB points down, so it's going to sit on the negative y-axis. So that's going to be minus FGB, minus the magnitude. And don't stop at the equal sign, keep going. So we get equals MB ABY. Well, AB is this vector, and it also points down. So I have to write ABY as minus the magnitude AB. So what does this equation give me? Well, TB becomes T, FGB becomes MBG, the definition of the force of gravity, and then I have MB AB. Well, AB, remember, both the magnitude AB and the magnitude AA we can write as A, so I actually can write this as just MBA. And if we go back through to our other boxed equations, I can make exactly the same change up here. So that's not AA, but it's actually just A, meaning the acceleration of box A and the acceleration of box B are the same. So we have 1, 2, 3 boxed equations. Let's copy them to the next page, and then we'll solve our problems. So the problem was find the acceleration of each box. So they don't even want to know what the tension is. We could find it if we wanted to. We have enough information. Oops. Let's just look at our boxed equations. boxed equations. And notice what we have. We have two unknowns in the first equation, tension and acceleration. We have exactly the same two unknowns in the third equation. And then in the second equation, we have an additional unknown, which once we know the tension we can solve for. It's the normal force. So in fact, I don't really need to use equation 2 because all it's going to give me in the end is the normal force, and nobody asked me for the normal force. So instead, I just need to use box 1 and 3. So let's see. The basic step in algebra is you solve for one of the unknowns, you plug it in, and thus you eliminate it. So if we're asked for acceleration, then we want to eliminate tension. So let's do it here. So tension is going to be equal to ma times a plus mag sine of theta. So I've solved for tension in one equation, and then I plug it in to this equation. So I get MAA plus MAG sine of theta is equal to, other side of the equation is MBG minus MBA. So I was successful. You see, I eliminated T, and now I have a single equation that only has A in it. Well, I want to solve for A, so I group them together. So I get MAA plus MBA. I can subtract off the MAG sine theta, so I get MBG minus MAG sine theta. And then what do I get? Well, I get, I can pull out the A. And I find that the acceleration is equal to MBG minus MAG sine theta all over MA plus MB. That's my final answer. Let's plug in our numbers now, see what we get. Remember, it's sort of exciting now because we've written down an equation for a magnitude. This could also be written as the magnitude of the acceleration vector, either one of them. But it's possible with this minus sign here that I could get something negative, and then we'd find that everything we did was wrong. Luckily, we don't have to redo anything. We just say that it was wrong. So let's see. MB and MA. Well, MB was 8 and MA was 10, and our angle was 60. So let's plug that in. So the acceleration is equal to 8 kilograms times 9.8 meters per second minus 10 times 9.8 times sine of the angle, which was 60. And then we divide that by MA plus MB. Well, that's 18 kilograms. And what we get is approximately minus 0.36 meters per second squared. So it's negative. We found a magnitude is equal to a negative number. Well, that's no problem. We just state it at the end. Our assumption about the acceleration vectors was wrong. The block slides down the incline, and MB goes up. So the acceleration is the block is sliding down the incline, and MB is going up. Since it's an acceleration, we really should say that it's accelerating down the incline and the block is accelerating up, which means that if you released it from rest, if it had a zero velocity, then it would start to move in that direction. But it's possible that you could be you could give it some velocity and it would just accelerate that way. So it would change the velocity in that direction. So that's our answer. And magnitude of A for both of them, which is equal to magnitude of block A and magnitude of block B, is 0.36 meters per second squared. So the magnitude we found and the direction we chose initially was wrong, but we just state that in the end. And that's it. So next time we'll deal with some more examples, specifically those having to do with friction.